Theoretical physics is a branch of physics that deals with the development of mathematical models and frameworks to explain and predict the behavior of the physical universe. Theoretical physicists use a variety of mathematical and conceptual tools to construct models and hypotheses that describe the fundamental laws of nature and the behavior of matter and energy at a wide range of scales, from the subatomic to the cosmological. Theoretical physicists often work in collaboration with experimental physicists, who perform experiments to test and validate their theories. Together, theoretical and experimental physicists work to advance our understanding of the fundamental laws of nature and to explore the mysteries of the universe. Without our understanding of the underlying mechanism of the nature, all kinds of today technology would be impossible. For examples, communication networking, global positioning system, GPS, high-performance computer and magnetic resonance imaging. The Institute for Fundamental Study, or IF in short, was officially inaugurated on March 14, 2011 by Naresuan University Council as a research center unit. From the first day to the present, IF members are working on the cutting-edge areas of research in theoretical physics to expand the boundaries of our understanding of the fundamental laws of nature, including cosmology, gravity, string theory, quantum information science and mathematical physics. We would like to emphasize that frontier research in theoretical physics is essential for advancing our understanding of the universe and developing new technologies that would benefit not only Thailand but the world society.
Okay, good afternoon everyone and welcome to Tah Poe Seminar Series 59, and today is the first talk of this series and we glad to have Pichet to tell us about duality-symmetric D3-brane action with twisted self-dual to form doublet. Please welcome our speaker.
Hi, good afternoon, everyone. Thank you, Dr. Pongwit, for the introduction. So basically, today I'm going to talk about the construction of D3-brane action in the Zen formalism, which is based on my recent work. Okay, so I will first talk about the motivation of how to construct the action of the basically duality-symmetric action, and then set up the notation, and then describe the linear twisted self-duality action in the Zen formalism, and then generalize to nonlinear action, and then talk about the construction of the D3-brane action, and then give a conclusion. So for the motivation, so if we consider Maxwell equations in free space, and we make a transformation basically from E to B and B to minus E, then these sets of equations remain the same. And more generally, if we make the internal SO2 rotation, which is also called the duality rotation, then it can be seen that the Maxwell equations can still remain the same. Okay. So we are basically interested in the kind of the duality rotation which leave Maxwell equations or the generalization of this invariant. Okay, we'll talk about generalization later. So recall that the Maxwell equation, if you write in terms of electric field and magnetic field, it looks like this in equation 3, where electric field and magnetic field can be written in terms of the gauge fields. So already from this equation, we have got the Bianchi identity, which corresponds to two of the Maxwell equations. And in order to get the other Maxwell equations, we basically vary the action with respect to the gauge fields. Okay. And if although the Maxwell equations are invariant under the duality rotation. The action itself is not. So, I mean, if we try to directly apply the duality rotation directly, we will see that the symmetry only realized only when cos 2 theta equals to 1, which means that just only the trivial case. Okay. So the natural question would be, can we make the duality symmetry manifest at the action level also, not just only limited to equation of motion level? And the quick answer is yes, but we need to introduce extra pair of electric and magnetic field. And for this, we will first discuss at the equation of motion level with the two sets of the fields. And then we will next discuss how to construct the action. So, so at the equation of motion level, so let's say we define another pair of electric and magnetic field, D and H, okay, and which would be related to our original E and B. And these kind of relations are called constitutive relations. And we can also the gauge fields corresponding to these dual electric and magnetic fields, okay, and we call them these dual gauge fields as C. Okay, we can see that the D and H automatically satisfies Bianchi identity, which is equivalent to equation of motion of E and B. And we also previously have the Bianchi identity for E and B. And these three equations will be important, and we have to keep in mind when we construct the action that we will want the on-shell description to describe these equations, basically. And the constitutive relations and the Bianchi identities that I have presented in the previous slide, they are invariant under this duality rotation. Okay, the same one as that I have shown before. Okay, so we may make a nonlinearization of the theory. The idea is to generalize the original action to be nonlinearized so that the constitutive relations is modified. I mean, the form of D and H in terms of E and B are nonlinearized. However, the equations 9 and 10, which are just Bianchi identities, they should remain the same. And it is convenient to define the field strength F and the dual field strength G, as well as the gauge field A and dual gauge field A hat. And actually, we cannot just randomly construct introduce the nonlinear terms into the action, because our randomly generated action might not have duality symmetry at the equation of motion level. And in order to ensure the duality symmetry, we need to impose we need to make sure that it satisfies Galliot-Sumino or GZ condition. Okay, which is given by equation 16. So this is for, I mean, for any nonlinear theory, okay, should satisfy this equation. And other generalization could be that we may couple to curve metric. We may also couple to axion and dilaton fields. And in these cases, I mean, in the case where we couple to axion and dilaton field, the duality symmetry group is enhanced from SO2 to SL2R. And we may also couple to a pair of two-form sources, in which, in the context of D3-branes, this pair is the B2 and C2 in the supergravity background. Now, let's just discuss how to construct the action that is manifestly duality invariant. And let me talk about just only two kinds of constructions. The first strategy, one of the strategy is that you construct an action with A and A hat as independent fields. And so the hierarchy identities are satisfied automatically, which means that what we require at the equation of motion level is that we get constitutive relations as equation of motion. However, the problem we have to solve, and one has to solve, is that constitutive relations are first order PDE in the gauge fields, whereas the equations of motions are second order differential equation. The idea for the construction is in the PST formalism. The idea is that the action that is constructed has to have a special kind of gauge symmetry, which allows one to realize that equation of motion is equivalent to first order PDE. Okay? And this has already been done in the past, and the extension to duality-symmetric D3-brane action has also been done in this formalism. But this is not what we are going to talk about in this talk. What we are interested in is actually an alternative strategy, which is that we are going to construct an action where F and G, the action of F and G, which they satisfy constitutive relations, okay? And so that the constitutive relations is already satisfied. So at the equation of motion level, we should realize that the F and G are field strengths of the gauge fields and the dual. The idea of the construction, well, maybe one of the idea is by following the Sen formalism, which is inspired from string field theory and whose direct application is in chiral form theory, which can be thought of as a cousin of duality-symmetric theory. And in this formalism, actually, the situation is a bit more complicated than what I explained here, because actually, the F and G are actually not independent fields. We don't vary with respect to F and G, because F and G composed of other fields, which is to be described later. And this theory also describes the ghost degrees of freedom, which is uncoupled from physical degrees of freedom. And the theory also has got two metrics, coupled to external two metrics. One is the standard metric, the metric that we are required, and whereas the other is the metric that is coupled to the ghost. And these are the constructions in the chiral form theories. And the action to the duality-symmetric D3-brane can be, in this talk we will talk about the application to the duality-symmetric theory and also to extend to the duality-symmetric D3-brane. So as I have mentioned, that the goal of this talk is to talk about the construction of the actions in the Sen formalism, which are the duality-symmetric action with nonlinear twisted self-duality condition, and this condition is equivalent to the constitutive relation. And we will also describe the duality-symmetric D3-brane action coupled to background type to be supergravity. Okay, so now to the setup. So let's just collect the gauge field and its dual into two tuple. And similarly, we define the two tuple of the F and G. And we define the vector U1 and U2 as the vectors corresponding to the first and the second components of the tuple. So we can write the vector A and vector F in this way. And differential form we define in this way. So the kind of like everything comes from the right instead of the standard ones defined in mathematics. And we also define two tuples of P form. So basically, this kind of quantity has got the differential form part and also the tuple part, okay, or we may think of as the doublet of the P form. And there are important maps on the space of the two tuples. One is the symmetric bilinear map M, which corresponds to the symmetric matrix Mij. Basically, the components of M contains the axion and dilaton. Okay. And there are also antisymmetric bilinear map omega, which corresponds to antisymmetric matrix. Basically, just Levi-Civita symbol in 2 dimensions. Basically, that omega 1, 2 is equal to 1. Omega 2, 1 is minus 1, and omega 1, 1, omega 2, 2 are equal to 0. And we also define the map J, which can be obtained from omega and M. And this is also important for the construction. So the Levi-Civita symbol, we use the epsilon to describe the Levi-Civita symbol, and with epsilon 0, 1, 2, 3, with our upper indices equals to 1. Okay. Hot star, we use the bullet. Okay. And this is how we define the hot star, which we use the standard metric to raise the indices, and so also the square root minus g is with respect to our standard metric. We reserve the star notation for this operation, which is acting on the tuple P form. Okay, so the bullet, basically the bullet acts on the P form, whereas the J acts on the two tuple part or two tuple basis, if we like. We define the wedge product of the two between two tuple P form and two tuple Q form in this way, where we make a wedge product between the the differential form part, and make a tensor product between the basis of the two tuples. So now let's discuss linear twisted self-duality in the Zen formalism. Yes, but unfortunately, I did not write it down. But basically, the J matrix will be will be the product of omega and M up to some I don't know up to some sign. But the feature that I would like to talk about is that J would contain the axion and the dilaton. I mean, each component of the J. Okay, so now, as I have mentioned before, that the original construction of the Zen formalism was inspired from the string field theory, which then was used to construct a covalent type 2B supergravity action. Okay, and the direct application has been on the construction of self-dual form series or the chiral form series that I had mentioned before. Okay, and all these iterations can be done. And even to get the M5-brane description, the application to the duality-symmetric theories is I would say just slightly less direct, and I believe that there are just not many references has done before. So let's describe the Zen formalism for the twisted self-dual theory. Let me explain the physical system that this formalism describes. which means that we are considered at the equation of motion level. So for the linear theory, the field strength doublet, which is defined as vector F equals to d vector A minus vector X, okay, where recall that X is two tuple form external field. So this equation should satisfy the twisted self-duality condition. So basically, vector X is star, vector F is star, vector F. And this equation is equivalent to constitutive relation. And this can be proved directly. And in the system, there are two sectors which are uncoupled from each other. There is a physical sector in which the two tuple gauge field, two tuple one form, is coupled to external fields, which are external metric, external dilaton, external axion, and the external two tuple two form field. And there is also the unphysical, or we may call ghost sector, which in which we have got two tuple one form A bar coupled to external metric dilaton and axion. And note that the fields in this sector, we have we introduce a notation bar to distinguish from the physical sector. Now let's come to the action level. Okay, which means that one of the requirements for the action level is to get the equation of motion which describes the system from the previous slide. So in the action level, the physical one form doublet and the physical one form and the ghost one form doublet, they are actually not independent fields. And actually not even their field strengths are independent fields. The independent fields in the theory are actually the one form doublet vector P and the two form doublet vector Q, where the two form doublet vector Q satisfies the twisted self-duality condition with respect to the bar field. Okay, and we define the bullet bar and J bar similar to that of the physical sector, but we use the bar field. And for convenience, one has got the composite field vector R, which is a function of all the fields. Function of the independent fields as well as the external fields. And this one has to satisfy the twisted anti-self-duality condition, okay, with respect to the bar field. And there is also the composite field H, which is defined as vector Q minus vector R minus vector X, and satisfies the twisted self-duality condition for the physical field. Okay, and these equations, especially these two equations, these three equations can be solved explicitly, and is shown in the lecture in the paper. So we can simply write down the action. This action is very similar to the action from the chiral form theory. Okay, but just by some inspection, we can just simply write down this action. Okay, or if we want to express in the indices of the two tuples that explicitly, we may have got this form. Or we can also write the equation which contains just only P and Q and coupled with the external fields. Okay, but it's gonna be a bit complicated, but it's also shown in the paper. One of the first checks is to check that the theory that the action has got a SL2, R duality. Okay. So basically, if we transform the P and Q and vector X by using the matrix, and also collect the axion dilatons into the tau and tau bar, and then use the Mobius transform, then apply these transformations into this action. Then we can show easily that the action is invariant under this transformation. Okay, and actually ABCD has to satisfy this condition also.
To be honest, I kind of lost.
Yes.
Can you go back and can you tell me can you tell me the gate field? What is the field strength of the gate field or sort of that?
Okay, so
the gate field A and A hat, right?
Yes.
And then
Yes.
What is it embedded into?
Okay.
Which part of your
Yes. Okay. Good question. So actually, if we ask for the gauge field and its field strength, it's actually still not seen at this level yet. We will see it at the equation of motion level. So this is actually the contrast between the strategy, the strategy 1 and strategy 2. I mean, the strategy 1, we would start from the gauge field and its dual as the independent fields, but in here we don't. Okay, basically, and things get even more complicated because the physical degrees of freedom are not independent fields. Okay, this is one of the features of the Zen formalism that makes life a bit complicated. Okay, so yeah, so basically these are not gonna be, yeah, I mean, the physical degrees of freedom are gonna be composed of these independent fields, basically. Yeah, so now we come to the equation of motion level. So if we vary the action with respect to P and Q, we get equation 33. And so we can solve the first equality by basically make the integration and suppose that the space-time has got no hole. So that we have got a new 2-to-1 form, okay, which satisfies its field strength, the field strength of psi plus P satisfies the twisted self-duality condition with respect to the bar fields. And also the equation 33 also implies that H is closed up to the presence of the external vector X, so that in the space-time without holes, we can have this form of H. H is exact. Okay. So now, if we like, we can say that at equation of motion level, we can recognize psi plus P as the unphysical 2-to-1 form, whereas psi minus P we can recognize as physical 2-to-1 form. Okay, yeah, just as I'm describing here, psi minus P is the physical gauge field doublet. Whereas psi plus P is recognized as unphysical gauge field doublet. And actually, to call them being physical or unphysical at this point is still not clear until we make the Hamiltonian analysis, which I'm not going to talk about this, but it's shown in the paper. The idea of the analysis was that to eliminate the fields by using second-class constraints equations, and then we will end up with the form of the Hamiltonian which separates the contributions from physical fields and unphysical fields, and so that the sign of the kinetic term of the physical fields is the correct sign, whereas the contribution from a physical field has incorrect sign of the kinetic term. Now, let's just talk about the generalization to nonlinear theory. So in order to generalize the nonlinear theory, what we want to do is to generalize the linear twisted self-duality condition to the nonlinear condition. Okay, which we cannot write this just randomly. It has to satisfy some consistency condition, and in this case, it should be equivalent to constitutive relation. Okay, whereas the equations of motion should still be the same. I mean, in the sense that we should still get that, for example, h is closed up to the presence of x, so that at the equation of motion level, we can still recognize that h is field strength. Now, if we consider again the nonlinear twisted self-duality condition, and if we write h equals to the doublet of f and g, then we should be able to express in terms of this equation where g tilde and f tilde are the duality with respect to the physical metric g, and a and b are the functions of f. Yeah, just only f. Only big F, not only big G, okay? Big F and as well as external fields, and in such a way that the G-set condition should be satisfied. Okay, so this is the what we want to solve. But the first, I mean, before that, maybe it would be better to try to simplify this form a little bit, maybe by imposing some answer. And the criteria to get the answer is to demand that the equation itself has got SL to R duality symmetry. So which means that both sides of this equation should transform the same way under SL to R duality symmetry. And it turns out that even if the field H is a composite field and also nonlinear, and its form is in general very difficult, or if not, if possible, I mean, to write down. Okay, but it is possible to show that H transforms linearly under the SL to R duality transformation. Well, at least I have shown that this is true up to any perturbative level. Okay, so it is, so this condition is quite non-trivial in the sense that in the sense that I have just described. Okay, so since H transforms linearly, we can immediately construct invariants, and it turns out that there are two invariants, two SL to R invariants, which are the basically the trace H square and the trace H to the fourth, where these are appropriately making the trace with respect to the physical metric as well as the internal tuple index. And furthermore, it can be shown that star of vector H and the H cube, which is defined in this way, also transform linearly under SL to R duality transformation. Okay, which is this. So we can just simply write down the form, the answer. Okay, so the left-hand side transform linearly. Okay, and the right-hand side for H and H cube also transform linearly. Okay, and the functions K1 and K2 should be invariant. So that's why they have to be functions of trace h squared and trace h to the fourth. And already from this equation, we obtain equation 50, which relates, basically relates trace h squared and trace h fourth, which means that we can now say that K1 and K2 only depend on one of the invariant, which we choose to be trace h squared. And now we demand that this equation should be equivalent with the constitutive relations. Okay, this gives us two equations. And also we demand the dz condition should be satisfied. And now we have got three equations, okay, of four variables basically. So the four quantities we have are A, B, K1, and K2, which means that we can eliminate, let's say we can use two of the equations to eliminate two quantities. And then we end up with one equation relating two quantities. And that one equation is this equation, which relates K1 and K2. And we can define the K as a function which, we can write K1 and K2 basically in terms of the function K. And so the nonlinear twisted self-duality condition, which is self-consistent and also consistent with the constitutive relation, is given by equation 56. Okay, so if we change the form of K, K is a function of trace h squared. If we change the form of K, then it means that we are describing different theory. Okay, but the exception is when K equals to 0, which we see that this is the singularity in the equation. And also there seems to be also another singularity at trace h squared equals to 0, but actually this case is removable because the case of trace h squared equal to 0 is the case of linear duality-symmetric theory. So which means that the perturbation around h squared equal to 0 means that we allow the linear theory, basically. So we can even write down the perturbed nonlinear twisted self-duality condition. Okay, and then from the form of the nonlinear twisted self-duality condition, basically we can derive the identities which leads to the function which is called u. Okay, and this function u will appear in the action later. Okay, but the key idea is that we have got this this identity. With this identity and the requirement that and the requirement of the form of the equation of motion, okay, then we can write down the action. So the action will contain terms that are kind of like this also. Okay. And yeah, more explicitly. Okay, so yeah, so this is how the u appears in the action. Okay, as I have described. Okay. I would say that although the first line looks the same as the linear theory, the R and H would be different functions of Q than the linear theory. Okay, and it would be even more complicated than in the linear theory. Okay, but formally the form looks the same. Okay, and we also have, if we like, the potential U. So, which satisfies the equation that I described earlier. Okay, and recall that P and Q are independent fields, and these fields tau bar x, g bar are background fields. Okay, composite fields satisfies the same relations, but with the nonlinear twisted self-duality condition. And also the function u can be written in terms of k, basically. Okay, so with the action written down, we have to check that the action we have has got required properties. So the first property to check is that it is invariant under SL2R duality transformation, and this can be shown perturbatively up to arbitrary order. And the action is also invariant under 3 types of diffeomorphisms. Basically, because the diffeomorphism transformation, I mean, because of how the field is defined, I mean, for example, here H is twisted self-dual with respect to star, but Q and R is with respect to star bar. So we would expect that the G and G bar get mixed in the action level. So that's why the diffeomorphism is quite complicated. Okay, but it had been shown at least in the case of chiral form theory, and it's actually also remain true in the duality-symmetric theory, that there are 3 types of the diffeo. So the first type is the standard diffeo transformation, which means that all fields transform using just Lie derivative, the standard Lie derivative. Okay. The second type is the zeta transformation, which basically transform physical fields. And the transformation on the physical field reduced to the Lie derivative at the equational motion level, whereas unphysical fields do not transform under this diffeo. And there is a chi transformation, which is the difference between the standard and the zeta transformation, and where we have to set the parameters the same. Okay. Another property is the Hamiltonian analysis, where we have to, where it can be shown similarly to the case of linear theory. And again, sorry, I'm not going to show it in this talk, but the upshot is that the separation of physical and unphysical sectors can be realized, and the sign of the kinetic term of physical and unphysical sectors are also kind of similar to the linear theory. Okay. So now, as I have mentioned before, that different K would correspond to different theories. So let's just talk about examples. So of course, the linear twisted self-duality condition, I mean the theory with linear twisted self-duality condition is realized if we set K equal to 1, okay, which leads to U equal to 0. And we can also construct the series with nonlinear twisted self-duality condition, at least as a perturbation to the linear theory. Okay, so basically we can make the basically perturb around the linear condition. Okay, and with these conditions, we can work out what was the action for one gauge field. Okay, which is given in this form. Okay. Actually, alternatively, we may do in the reverse direction, which means that we start from the one gauge field theory, and then we work out what is the K corresponding to the duality-symmetric theory. Okay, so for example, the one gauge field theory that we are interested in is the DBI action. And we may work out in the reverse step as the previous slide to obtain the form of the K and also the form of the U, which means that we are finished writing down the nonlinear self-duality, nonlinear duality-symmetric action in the Sen formalism. So which the DBI-like action can be extended to the D3-brane action, okay, in the Sen formalism. So we are going to describe the construction of the complete D3-brane action in the Green-Schwarz formalism, which means that the supersymmetry is in the background field, in the background theory, background supergravity theory, whereas the fields on the D-branes are bosonic fields. Okay, but the supersymmetry is induced onto the world volume. So for the background target space or background type to be supergravity, these are roughly speaking the field contents. So we have got the coordinates, so which are basically supersymmetric coordinates. So it consists of the bosonic coordinates, 10 bosonic coordinates, and 32 fermionic coordinates, which can be, the details doesn't matter in here. And we also have superview-bias, which are basically the supersymmetrization, if you like, supersymmetrization of gravity. And we have got dilaton superfield, which means that we have got dilatons as well as their superpartners. We have super NS and SB field, which is B2. We have got super Ramon C fields, which are C0, C2, and C4. Well, what we are interested from here is that the constraints, I mean, these fields have to satisfy several constraints, and these are the constraints that we have to take into account when we discuss our construction of the D3-brane. Okay, and basically I just pick this result and then just make sure that the D3-brane being constructed basically satisfies this, I mean, especially consistent with the constraints basically. So for the field content on the D3-brane world volume, so the standard D3-brane world volume field is the gauge field. Okay, and it also coupled to the target space superfield through the pullback. Okay, for example, the metric is the pullback from the background metric, and the world volume field strength, okay, is in this form where B is the pullback of the NS super B field. Okay, so we can identify the vector X from the previous section as the tuple of B2 and C2, and then appropriately introduce the term part of the Wessel-Minot term. Okay, we can end up with the D3-brane action in the Sen formalism. But we will have to make the consistency check as well. So basically the symmetries, okay, the important thing is to check for the symmetry. So we have shown previously that this kind of action has got SL2R duality symmetry and also the diffeomorphism. And also it has got this kind of gauge transformation, which we may say that is the gauge transformation on the P and compensated with the transformation on other fields. And also by construction in the Green-Schwarz formalism of the embedding, the D3-branes has got, I mean, the theory has got too many fermionic degrees of freedom. We should be able to realize, we should be able to recognize that actually these extra fermionic degrees of freedom are actually get projected out due to the symmetry, which is called the kappa symmetry. And it is important to check that the action has got kappa symmetry. Otherwise, the supersymmetry is not realized. And basically, we can just write down the kappa symmetry transformation. Okay, but I mean, by requiring that the action should take this kind of form. Okay. Okay, so basically, if we make a transformation by equation 72, then we get this form in equation 73. The important ingredient is this gamma bar matrix, which is different for each different theory or different formalism. Okay, but this gamma bar matrix has to have to satisfy these properties. So gamma bar equal to 1 and trace of gamma bar equal to 0. So with these properties, we can define the projectors. Okay, so basically 1 minus gamma bar divided by 2 is a projector, as well as 1 plus gamma bar divided by 2 is also a projector. And also, in order to, for completeness, in order for the variation to vanish, we should also set this to be 1 plus gamma bar times the kappa. So, because this is a projector, we have to, so in order for this to vanish, I kappa epsilon has to be contains the projector in the basically in the perpendicular direction, internal direction. Yeah, which means that we require to have the structure of 1 plus gamma bar, okay, and then also multiply by kappa, which is the spinner, okay, because this is a spinner. Okay, so with this construction, this is what ensures that half of the component of the kappa can be used to gauge away some of the fermionic degrees of freedom, and in the end allows us to realize that bosonic and fermionic degrees of freedom match. Okay, so as a conclusion, so we have discussed duality symmetry, constitutive relation, and how to enhance SO2 to SL2R by introducing axion dilaton, and also discuss how to construct the Sen action for linear twisted self-duality condition and also the non-linearization, and also discuss the important application, which is the construction of duality-symmetric D3-brane action in the Sen formalism. So as a future work, maybe to extend the construction to describe the system which originally has got more than one physical gauge field. Okay. Because everything in this talk is that the original theory has got one gauge field, but now if we can extend to describe more than one gauge field, then this would be good. Okay, so this is all. Thank you.
Any questions? Please.
Maybe basic questions about what is the string fields and how it motivates the Sen formalism.
Oh, good question. Actually, I haven't looked at this basically, but the string field theory is, for the string theory, we can think of that we make a quantization of a single string. But string field theory, we think of the field of strings, which is even more complicated than the, for quantum field theory, we may think of like quantization of field for point particles, basically. But string field theory is like the quantization for the field of strings. And I believe that this will give you some conditions from the quantization, which I believe which say that actually the fundamental fields are actually the P and the Q fields. Sorry, it's a bit complicated.
one slide, I think you have the condition of like, I don't know, the dual field, and there is a field is unphysical and another one is unphysical.
Okay, yeah, good question.
Around
Yeah.
that, how can you tell that this one is physical and this one is unphysical?
Yes, good question. So actually, we cannot tell at the equation of motion level. We should make a check at the Hamiltonian level, which unfortunately I don't show it in the slide, but that is in the paper. So I mean, basically, you make the Hamiltonian constraint analysis, and then you realize that you get a second-class constraints, and then you solve these second-class constraint equations to eliminate some of the fields, and then you end up with the phase space, which is reduced. And basically, the Hamiltonian in the reduced phase space is separated into two parts, basically. One part is, let's try the kinetic term for one of the field. Yeah, and the other part is the kinetic term of another physical, of another field. And then the kinetic term of of the field, which corresponds to physical field, has got the correct sign, whereas the other term has got incorrect sign. So basically the kinetic energy is negative. Okay, so we interpret the field in that contributes to that term as unphysical field.
So at the beginning, you don't know which part is physical or physical at first.
Yes, because it's really complicated. I mean, this kind of construction is that the independent fields are the P and the Q, but the physical field I would say that the physical field is actually the H, which we can recognize only at the equation of motion level. But the H itself is that there is a mix between physical and unphysical part, off shell, and is quite complicated, I would say.
So how we ensure that one part is unphysical, one part is physical, because it may be physical.
Okay, so actually, yeah, we I would say, consider the phase space of the full theory. Okay, so for example, we have got P and Q, and also their conjugate momenta. Okay, so this form the full phase space, but there are constraints on the phase space, which means that the dynamics occurs on some of the surface, which is called the constraint surface. And I mean, if we consider everything in the full phase space, everything, I would say everything is quite mixing and very confusing. But if we just only come to the or just only consider the constraint surface, which what we do actually is to solve the second class constraint equations to eliminate some extra variables, so that the constraint surface is now the reduce of the phase space. And in this reduced phase space, there is no more constraints, and everything is no longer tangled anymore. So in this reduced phase space, things are now separated, basically. Yeah, so the Hamiltonian in this reduced phase space is now separated into two parts, and we can see directly that it's separated, and there is no interactions between the two parts. Yeah, but if we look at the full phase space and with constraints, then it's hard to tell.
Okay. Okay. You present about the sense formalism that that is the framework in general. Let's say that you try to uh, formalize the duality via the sense formalism here, and I just would like to ask what is the specific let's say like specific property of the D3-brane, and I mean that is different from in general construction in sense formalism. I mean that apart from the 4D, I'm not sure.
Okay. So, I mean, for the original sense formalism, the direct application is to the chiral form theory, or someone would also call it a self-dual theory, which are theories in, for example, 2 dimensions, 6 dimensions, 10 dimensions. For the theory in 6 dimensions, we can extend to describe M5-brane. But here we try to apply it to duality-symmetric theory, which is the theory in four dimensions. So which direct application is on the D3-brane? Do I answer your question?
I mean, I know that it's for 4 dimension, but is there any specific criteria that D3-brane need to be in this way, apart from in general for the formalism of the sense formalism there? Do you get my point? I mean, I'm not sure is that for sense formalism it made for general D dimension, right?
Okay, good question. It works for 4 dimensions.
4 dimension.
0 dimension, I guess it would work, but the differential form would be different, and the 8 dimension would also work with different differential form. The most useful is 4 dimensions, I would say. If you like, you may want to construct the 8 dimension, but I don't know if there is some corresponding theory in the string theory.
Oh. Okay, and thank you everyone for participating, and thank again for Ajahn Pichet to give us a wonderful talk today. Thank you.
Thank you.
That will be the end of today.